Welcome all of you in the semester 2, and we are going to start paper number 5 of semester 2, and it's a partial differential equation. In the previous semester, the fifth number paper is what? Ordinary differential equation. And what is the difference between ordinary differential equation and partial differential equation? That in the ordinary differential equation, uh, dependent and independent variable are single. That is one independent variable, independent variable. But in partial differential equation, the dependent variable is one, but the independent variables are more than one. So we are going to start the partial differential equation, paper number 5, partial differential equation. The first chapter is ordinary differential equation more than two variables. So this is the first chapter, and simultaneous differential equation of this is the simultaneous differential equation of first order and first degree, dx by p, dy by q, and dz by r. So we in this chapter will see the methods to solve this type equation, that is simultaneous differential equation of first order and first degree of the form dx by p, dy by q, dz by r. Where what are pqr? Pqr, the capital these pqr are the functions of x, y, z. And if the relations u1 xyz is equal to c1 and u2 xyz is equal to c2, the two integrable solutions of this equation number 1, that is this dx by p, dy by q, dz by r, then these two relation forms the general solution of 1, or it is called complete integral of 1. That is, we have to find the solution of general solution of this differential equation. For that, find two relations, two functions u1 xyz is equal to c1 and u2 xyz, that is the function of xyz, is equal to c2. The two integrable solution of 1, that is that find two solutions of this equation number 1, and this combinedly these two solutions of equation number 1 form the general solution of equation number 1. So we have to find the general solution of equation 1, then find two solutions of this equation number 1, and is also called general solution, or is also called complete integral of this equation number 1, or primitives of 1, or integral curves of 1. So the question on this topic is what? This type equation is given, that dx by p, dy by q, dz by r, and the question is find complete integral, or find general solution of the differential equation, or find the primitives of the differential equation, or find the integral curves of this differential equation. Okay. So method to solve this type equation, dx by p, dy by q, and dz by r. We have to find the solution, general solution of this differential equation. So there are some methods to solve these type equations. So first method is this. Suppose that one of the variable is either absent or cancelled from any two functions of the differential equation. That is, if you consider suppose the first dx by p, dy by q, and if one variable is absent or cancelled, that is if there is no z in the first two ratios, for example, or if you consider first ratio and third ratio, and if variable y is absent or we can cancel y, then what is the method? Then consider these two functions, fractions, not functions, fractions. That is suppose if you consider the first two fractions, that is dx by p, dy by q, and if there is no variable z in these two fractions, first two fractions, okay, then we consider that two variables. The z variable is absent in the first two fractions, or z cancelled, this function z cancelled from first two fractions. Then what is the procedure? Then consider these two fractions, and from these two fractions obtain one integral solution by integrating both sides, or some another procedure. That is, if the equation is either uh, homogeneous, non-homogeneous, or is a linear differential equation, then apply that procedure and find its solution. Okay, and if the one variable is absent in the two fractions, then the equation becomes a ordinary differential equation in two variables. Okay, so by applying the procedure of solving these this differential equation, solve this differential equation and find one solution, and that is one integral or one solution. That is, we have the u1 xyz is equal to 7. That is, we have the one solution of that equation. Then I have to find the another solution of the same equation. So by integrating both sides, same procedure can be repeated with another set of two fractions. Suppose we have the another two fractions of the same type, that is one variable is either absent or cancelled. Then we consider that two fractions and find a solution of that from that two fractions, and that is the second solution or second integral of the given differential equation. And these two solutions gives the general solution of one or complete integral of equation number one or the given equation. When one integral can be obtained by this method and the second integral, that is solution, is difficult to obtain by this method, then known integral can be used to obtain the another solution. That is, if we find, suppose the first one solution of the given differential equation by this procedure, that is by considering two fractionals, and if the second solution is obtained by using this method is difficult, then we apply the another procedure, that is we use the first integral or first solution to obtain the second solution. So this is the sub method of equation number method number one. This is the sub method. This is the main method, and this is the sub method. That is, in the order to find the second integral, second solution, use the first obtained integral or solution. Okay, so this is the suppose we say it is a sub method of equation method number one. And the method number one, method number two, that is, if the method number one fails, then apply method number two. That is, choose multipliers L, M, N such that each ratio is equal to, that is, if we multiply by L to this dx, M to this dy, and N to dz, and if we multiply L P, M by Q, and N by R, and adding, that is, each ratio is equal to L dx, right? This is L dx M dy plus N dz divided by LP plus MQ plus NR. That is, choose or find these multipliers LMN such that this ratio, in this ratio, this LP plus MQ plus NR is 0. That is, find these L values of LMN. These obviously these are the functions of x, y, z, or LMN are constants. And multiplying by using this LMN, we have this LP plus MQ plus NR is equal to 0. If this happen, then we say each ratio is equal to L dx plus M dy plus N dz divided by 0, means L dx. Therefore, we have L dx plus M dy plus N dz is equal to 0. And this is the exact differential equation, or this is equation of another type. This is the exact differential equation. Therefore, there exists a function, or there exists a solution of this differential equation. There exists a function u x y z, u of x y z, such that du is equal to L dx plus M dy plus N dz, and then du is equal to 0. Means after integrating, we have u1 xyz is equal to c1. u1 xyz is equal to c1. That is, we have the one solution or one integral of the given differential equation number one. And then, in order to find the second solution of such a type of differential equation, we may apply the same procedure. That is, obtain or we find multipliers LMN, another element, but the multipliers must be linearly independent of the multipliers LMN. That is, the new multipliers must be linearly independent with the first multipliers LMN. Okay, so find another set of multipliers, obviously linearly independent subsets set of multipliers as above. That is, by using the same procedure. That is, we have LMN, find LMN such that LP plus MQ plus NR is equal to 0. And again find the second solution by using the same procedure by integrating. We have u2, suppose we have e2 xyz is equal to c2, and this is suppose the second solution. Then combinedly these two solutions u1 xyz is equal to c1, u2 xyz is equal to c2 form the general solution of the given differential equation or complete integral of the given differential equation. Suppose if the we can apply the first method for one solution, one integral, and the second method for the second solution or second integral of the given differential equation. That is, we find first solution of the given differential equation by first method and the second solution by second method. So we can apply combinedly these two methods. If in a second set of multipliers is not obtained easily, so if the second solution, second multipliers are not obtained easily, then we may use first method to obtain the second solution. That is, uh, uh, in order to find the two solution of this differential equation, we apply mixed method. That is, for one solution apply method 1, and for another solution apply method 2. Okay, so combinedly or independently we can solve the given differential equation, simultaneous differential equation, dx by p, dy by q, dz by r. So these are the basic two methods to solve the simultaneous differential equation of first order and first degree of this form, dx by p, dy by q, dz by r. So we'll see the examples of such a type of differential equation. So question is what, or example is what, find the integral curves or find the general solution, find the general solution or find the complete integral or find primitives. So the question is what, find integral curves of the set of equations or solve the differential equation. This is also another question, solve the differential equation or find the general solution or find the complete integral or find primitives. And the differential equation is what, dx by y into z, dy by zx, and dz by dz by x into y. So this is the differential equation of the type dx by p, dy by q, dz by r. So p is what, p is yz, q is the zx, and r is x into y. Obviously p, q are the functions of x, y, z. So consider this first two ratio, because what happened, this z, after cancelling this z, what we have, dx by y, dy by x, and this is what, these are the two fractions in which z, variable z is absent. So this happened. So when we consider two fractions, suppose one of the variable is either absent or cancel from two fractions, then the given differential equation, from the given differential equation, then consider these two fractions. Okay, so why we consider here the first two fractions, because the z variable is cancelled from these two fractions, and what we have then, after cancelling this z, we have dx by y is equal to dy by x, and then after separating the variables, that is shift this x to LHS, then we have x dx is equal to y dy. So this is the differential equation of variable separable form. So actually this is the differential equation of first order and first degree in x and y. So in order to solve the first degree equation of first degree and first order differential equation, we already uh, studied in the 1.T.Y.B.Sc class that first order, the differential equation of first order and first degree. So there are different types of the first degree, first order differential equations. The first one is what, variable separable form, is the type of the differential equation of first order and first degree. And then homogeneous differential equation, non-homogeneous differential equation, and a linear differential equation, Bernoulli's differential equation, exact differential equation. These are the types of the differential equation of first order and first degree. So in order to solve the first order and first degree equation, we have to apply the appropriate method. That is, if the first order first degree equation is of the type variable separable form, then what is the method? Separate the variables and integrate both sides. So this is very simple method if the variables are separated. So when we say the differential equation is in variable separable form, so this equation is variable in the variable separable form, because we collect the variables of x in LHS and the variables in terms of y in RHS. That is, if we separate the variables uh, in two sides, that is the variable of x in LHS and the variables of y in RHS, then we say the differential equation is in variable separable form. But if we cannot separate the variables, then apply the second method, that is either it is of the type homogeneous or it is of the type non-homogeneous. So there are some special methods to solve the homogeneous differential equation, non-homogeneous differential equation. If it is of the type linear differential equation, we know the basic type of linear differential equation is what? dy by dx plus pxy is equal to qx. The differential equation is of this type, that dy by dx plus px. What is px? Px is the function of x into y is equal to qx. Qx is the function of x, purely function of x. So if the differential equation of the type linear differential equation, then apply the method to solve the linear differential equation. So in order to solve these differential equations, we first learn all these types, that variable separable form, homogeneous, non-homogeneous, linear, exact, Bernoulli. So this is of the type variable separable. So separate the variables. So in LHS, all the x variables are collected. In RHS, all the y variables functions are collected, and then integrating both sides. So what is the integration of x? X square by 2, y square by 2 plus constant of integration, suppose c1 dash, then multiplying by 2. So obviously 2 c1 dash, suppose 2 c1 dash is c1. So x square is equal to y square, x square minus y square is equal to c1 is the first or one solution of the given differential equation, this simultaneous differential equation. Okay, then we will find the another solution, second solution of the same differential equation. So in order to solve the find the second solution, consider the ratio dy by this zx and dz by x into y. That is, consider the fractional number 2 and fractional number 3. So we have what we have, then y get x get cancelled, and then for dy by z and dz by y. So one variable is absent now, and then separate the variables. We have y dy is equal to z dz, and then integrating, what we have, integration of y is y square by 2, z is z square by 2, and add the constant of integration c2 dash, suppose c2 dash, and then multiplying by 2, and this c2 c2 dash is suppose c2. So y square minus z square is equal to c2 is the another solution, and therefore x square minus y square is equal to c1. That is this first solution, and this x square, and this another solution is what, y square minus z square is equal to c2, gives the general solution or forms the general solution of the given differential, gives the general solution of the given differential equation, or forms the, this combinedly these two solutions forms the general solution or complete integral of the given differential equation, or primitives of the given differential equation, or integral curves of the given differential equation. So instead of this, we can also consider the first ratio and third ratio. If you consider dx by y into z, dz by x into y, then this y get cancelled, and then we have the equation of the type dz by dx by z and dz by y. Okay, so we have the two solutions. Any two solutions, then we say that these combined these two solutions form the general solution. Another problem, solve the differential equation. So again is the of the same type, that dx by p, dy by q, dz by r. So this, if we shift this x to denominator, then we have dx by y square into z by x. So this is the of the form dx by p, dy by q, dz by r. So we have to find the two solutions of this differential equation. So consider the first two ratios, first two fractions, that is x dx by y square z, dy by zx. Then what happen? If we cancel z, then we have x dx by y square, dy by dx. That is, first method is applicable because one variable is now cancelled, and then we have the two variables only. These, if we observe this equation, then there are only two variables. There is no z. Okay, dx and dy, and there are x and y functions. All are the functions of x and y. So separate the variables. So we have x square dx is equal to y square dy. So, and then integrating, then we have x cube by 3 plus y cube by is equal to y cube by 3. And suppose c1 dash is the constant of integration multiplying by 3. And suppose this 3 c1 dash is c1. So this is one of the solution of the given differential equation. Then consider the first ratio and third ratio. This first and third. So what do we have? X dx by y square z is equal to dz by y square get cancelled, and then we have x dx by z is equal to dz. That is the variable. There are only two variables now, x and z. Okay, y is absent in this, and then separate the variables and integrating. We have x square by 2, y square by z square by 2, integration of x and z plus c2 dash is suppose constant of integration multiplying by 2, and suppose 2 c2 dash is c2, and then this x cube minus y cube is equal to c1, that is this first, and this is the x square minus x square minus z square is equal to c2, gives the general solution or forms the general solution, or or is the complete integral of the given differential equation. So we'll see the remaining problems of the same type in the next lecture.